The heart never sleeps, but its cells do get tired, and some of them get stuck in a strange, half-living state that scientists are now realizing may be silently undermining cardiovascular health from the inside out. These are senescent cells, metabolically active, no longer dividing, and often full of inflammatory mischief. Sometimes dubbed zombie cells, they accumulate with age, particularly in the heart and blood vessels, where their dysfunction may play a central role in the slow, relentless march toward heart failure, atherosclerosis, and other forms of cardiovascular decline. What makes this story especially complex, and far more interesting than the usual aging narrative, is the idea that senescence in the heart isn't just a blanket problem. It's a diverse, dynamic phenomenon with distinct cellular subtypes, different tissue locations, and wildly different effects. The question is no longer, are senescent cells harmful, but which ones, where, and how much? Two cell types in particular are under the microscope: cardiac fibroblasts and vascular endothelial cells. Both are abundant in the heart, both are highly responsive to stress and injury, and both are prone to becoming senescent as we age. But once they enter senescence, they don't all behave the same way. Senescent cardiac fibroblasts, for instance, are now thought to play a dual role in heart aging and disease. In healthy tissue, fibroblasts support the extracellular matrix, maintaining the mechanical integrity of the heart. But with age, or in response to ischemia, hypertension, or toxic insults, some fibroblasts go senescent. And that's when things start to unravel. These zombie fibroblasts begin secreting matrix metalloproteinases, pro-inflammatory cytokines, and fibrotic signals like TGF-SS, contributing to myocardial stiffening, impaired contractility, and interstitial fibrosis. The result? A heart that becomes less efficient, less compliant, and more vulnerable to failure under stress. But not all senescent fibroblasts are profibrotic. Some may have anti-proliferative effects that prevent maladaptive remodeling, while others might signal for tissue repair or angiogenesis after injury. This heterogeneity is exactly why the concept of senescent subtypes is so critical. With tools like single-cell RNA sequencing and proteomic mapping, researchers are beginning to tease apart which fibroblast subpopulations are the villains and which might still be playing a protective role. The hope is to develop subtype-specific senolytics or xenomorphics that selectively clear or quiet the destructive fibroblasts while preserving or even enhancing the function of the helpful ones. The story is similar but arguably more sinister when it comes to endothelial cells, which line the blood vessels and regulate vascular tone, inflammation, and permeability. Endothelial senescence is linked to virtually every step of atherosclerosis: reduced nitric oxide production, increased adhesion molecule expression, monocyte infiltration, and plaque destabilization. In aging vessels, senescent endothelial cells often cluster at branch points and areas of disturbed flow, forming pockets of dysfunction that accelerate plaque buildup and reduce vascular flexibility. Again, though, the diversity matters. Not all senescent endothelial cells are equally inflammatory. Some are metabolically dysfunctional, but not proatherogenic. Others become hypersecretory hubs, releasing SESB factors that not only damage the local vasculature, but influence distant organs through the bloodstream. Understanding which subtypes are present, based on transcriptomic, epigenetic, or metabolic signatures, could open the door to vascular-targeted xenotherapies that prevent or even reverse aspects of cardiovascular aging. There's also growing interest in how these senescent subtypes interact with the immune system. Senescent endothelial cells can suppress immune surveillance by attracting regulatory T cells or expressing checkpoint molecules like PD-L1. Senescent fibroblasts, on the other hand, may release chemokines that perpetuate chronic inflammation or prevent proper macrophage clearance. This immunomodulatory angle is especially relevant in older adults, where immune dysfunction and cardiovascular disease often travel together. The real excitement lies in what's next. Imagine a cardiac aging diagnostic panel that uses a small tissue sample, or perhaps just a blood-based biomarker profile, to determine your specific senescent cell landscape. Are your coronary arteries lined with SASP-heavy endothelial zombies? Are your myocardial fibroblasts pushing the heart towards stiffness and failure? Depending on the answers, your treatment plan could include senolytics that home in on vascular targets, or xenomorphics that calm inflammatory subtypes without harming structural integrity. These therapies are already in early testing. In animal models, Clearing senescent cells in the heart improves function after myocardial infarction, reduces fibrosis, and even restores aspects of youthful gene expression. The goal is not to eliminate senescence entirely, it's to rebalance the system. Aging hearts still need stress-responsive cells, temporary fibrosis during repair, and controlled inflammation. But when senescent subtypes linger past their welcome, or begin acting destructively, they become not just markers of aging, but drivers of it. So yes, the heart may accumulate zombie cells as it ages. But not all zombies are equally dangerous. Some are whispering quietly, others are shouting, and a few are trying to help. The future of cardiovascular aging lies in listening carefully to what each of these cells is saying, and responding with therapies smart enough to keep the peace, clear the noise, and let the heart keep beating strong.